Gus, thank you for coming to the NIH to film this history video for the Project Bionics. As you know, Project Bionics is a joint effort between the National Library of Medicine, ASAIO, and the Smithsonian Institute. It's been going on now, I guess, about 17 years. And it's important that we hear from pioneers like yourself on how you entered the field and what you'd like to share with young people and others as we go through this interview. So would you like to trace back a little bit and give us a little, students are often wondering, how do I get into the field, and how did this come about? How did you make decisions?
Sure. Well, first, John, it's my pleasure to be here. I'm honored to be interviewed as a pioneer. When I was in high school, I probably had more of an interest in automobiles and not really science or engineering. So when I graduated, I went to work, and I worked part-time at a gas station and did roofing and sheet metal. And I met a young engineer through an interest in automobiles, an engineering student at Drexel. And he knew all kinds of things. I mean, he knew about heat transfer, combustion processes. He made his own electronic ignition system. And I thought, boy, how does this guy know all this stuff? And I thought, he must, learn this through engineering school. So that's really what got me interested in engineering, because I realized that if you wanted to understand all these different phenomena that you see happening, that you had to go to school to do that. So that's how I got interested in engineering, and I went and got my bachelor's degree in mechanical engineering from Penn State. And while I was an undergraduate, I did some heat transfer research, and had read an article about bioengineering and had some interest in that, and started interviewing at different schools, University of Pennsylvania and Drexel, and I had decided to go to Drexel to work on a project doing liquid breathing. And about that time, Dr. Pierce came to Penn State and approached the engineering department and said he wanted to put a group together to build an artificial heart. And
now where did you say Bill came to there? Where was Bill at that time? Did he come from the NIH then?
Let's see. He was at the NIH, and then I believe he was University of Pennsylvania with John Waldhausen.
I see.
So John Waldhausen came to Penn State, Hershey Medical Center, and recruited Bill Pierce. And he had done a little bit of artificial heart research at Penn. And Bill was a chemical engineer, is a chemical engineer, and saw the value of working with engineers. Penn State did not have a bioengineering program at the time, and I was actually in the ROTC basic training course, and they came out and got me in the field and said, there's a doctor on the phone that needs to talk to you. And it was John Brighton. He was an assistant professor in mechanical engineering at the time, and said, would you like to work on the artificial heart project? And I said, well, I don't know. I'm going to go to Drexel and do liquid breathing. And anyway, it turned out the assistantship was more. And John assured me that within a few years we'd have an artificial heart, and I could just move on. So that's how. I think, there are a couple things that are important for students, and I think one is to be persistent. So even if you're told, I went through, really wasn't qualified to get into college. I hadn't taken, the SAT exam. And so they said, well, you could get into an associate degree program and then move into a bachelor's program. So the idea was I didn't give up. I was persistent. The other thing I'll tell students is that you have to have confidence in yourself. And the other thing is, I'll tell students, I think it was Yogi Berra said, I came to a fork in the road and I took it. And to tell students that when they see an opportunity, they shouldn't just freeze in place. They should really pick one way to go or another. So for me, it was seeing what an engineer did and really wanted to understand things. And then I had a choice where to go to do liquid breathing or artificial heart research, and I chose that.
So you were in graduate school then as well?
I did my master's degree then at Penn State on a mock circulatory system, which I think later was adopted by the NIH as a standard for testing. And then I did 6 months on active duty and came back to Penn State and did research on myocardial oxygen consumption and left heart assist bypass. We would ligate part of the hemiazygous vein and ligate the coronary sinus, and then collect the venous drainage through the hemiazygous vein and measure oxygen extraction and look at that as a function of assist, looking at tension time index and seeing how much you were reducing myocardial oxygen consumption.
Well, the group there was very powerful with John Brighton, yourself, with Bill Pierce. Who else was in the...
Wynn Phillips.
Wynn Phillips was there.
So all people that went on, John became department chairman at Michigan State, and then I think he was a chairman down at Georgia Tech, came back, was department head for engineering at Penn State, and then went on to be provost. And Wynn Phillips, I believe, is a provost at Florida. So, that's a lesson too for young people. Those were the people you saw in there on the weekend. So they were successful people. So working hard doesn't hurt at all.
Well, I use the same quote from Yogi Berra when I talk to my students. When you come to a fork in the road, take it.
Yeah.
Volunteer early.
Yes.
So how did the program evolve over time? Which leg started and things separated out?
Mm-hmm. Well, I started on my master's thesis in 1970, and then I did some research at Hershey a year, I think perhaps in 73 or 74, and then joined the faculty down at the medical center. So I had a joint appointment in the College of Engineering and the College of Medicine. And at that time, we were just starting on the ventricular assist device, the one that went on to be the Pierce Donikai, and then was purchased by Thoratec, I think, in 1984. But we did our first patient with that device in 1976, and actually had a survivor that year. So it was an interesting time because all you needed to do, this was pre-FDA, so you needed to satisfy yourself and the IRB, and so I think our IRB submission was probably about a quarter inch thick, and went ahead and did a series of patients with that device.
About how many patients do you think were treated that way?
I think we did about 80 at Hershey, and I think Thoratec at somewhere over 4,000 of those pumps were implanted in patients, and I think it's still manufactured today.
So what was the next step as far as now what was your master's thesis on?
That was on the mock circulatory system.
Mock circulation.
Yes.
Why don't you tell people about that? Because I don't think people realize how important that was to the the research program to have that?
Well, initially, people were making these devices and just sort of putting them in, in animals, and really had difficulty characterizing them. So various people tried to make different models of the circulatory system to characterize them. And they were very often very simple, just a plain column of water, or there was an incredibly complex one made by Hydrospace Research Corporation that was just too difficult for anyone to work with. So we came up with the idea that what we needed to do was to build something that would pretty accurately characterize the circulatory system, and to be able to model that and then build it and test devices. So it actually started with a computer model, but it was done with an analog computer, a ComDyna, analog computer, but it did do the.
It was an analog computer.
Right. Yeah. Yeah. It used a variable diode function generator to generate flow, and then measured, simulated the pressure. So we used that to get physical dimensions for the system, and then you could put an artificial heart or an assist device on that loop and test it for its hydrodynamic performance. So that was 1970 for the mock circulatory system, and then in 72 or 73, I did the research on myocardial oxygen consumption and ventricular assist, and then went down to Hershey and worked on the Pierce-Stonikai pump. That was made an international historic landmark by the American Society of Mechanical Engineers. So along with the Kingsbury bearing and other historic landmarks, so that was a very nice honor.
Yeah, that was a terrific recognition for the work that had been done by the group.
Yes, yes. And I think, one of the important things also is that Bill Pierce was able to establish an intercollaborative research group that worked with veterinarians, surgeons, engineers, and really was able to attract some very, very good people. And we've been able to continue that tradition for years. So, all the accomplishments that get sometimes attributed to one person really should be attributed to a lot of different people.
Of course. Why don't you tell us a little bit about how did the laboratory develop there in Hershey, and the animal facility and the various aspects of the program?
Well, the animal facility is a really interesting story. Hershey was a very new medical school. I think the first graduating class was 1970. I think it opened in 67, but when it was being built, Dr. Harrell was the new dean, and he had the foresight to say, we're going to build, this is a story anyway that I was told, we're going to build the animal research facility first, because if we don't do that, we get near the end, there won't be enough money. So it's a very nice animal research facility, and it's been maintained throughout the years. So when I got there were empty rooms. Physicians were in the clinic 50% of the time and doing research 50% of the time. So you had access to surgeons and clinicians in general, and you had laboratory space. It's a lot different today. We do have laboratory space, but getting access to physicians with them being so busy is difficult.
It's amazing, actually. So how did they design, as I recall in the animal facility, the rooms, the surgery rooms and the test environment, research rooms, quite large and very unusual for an animal facility?
Well, originally there was one operating room which really wasn't meant for large animals. So I'm trying to think of the year, probably in the late 1970s, Max Lang and Bill Pierce put together a proposal for the Kresge Foundation with Kmart. And they were able to secure funds to do a large animal wing. So then we put a large operating room where you could have a heart-lung machine, and there were some imaging equipment there, as well as recovery rooms. So that whole one back section then was due to the Kresge Foundation.
So you've now completed your master's degree, and now how did you get onto your PhD?
Well, I just had a real interest in the project, and at that time, people weren't sure, what was happening with a heart assist device. I mean, people talked about reducing myocardial oxygen consumption, but there hadn't been a whole lot of research into that area with actual heart assist devices. So that was my thesis to look at that, and we gained some data indicating that there were large changes in myocardial oxygen consumption, but they were primarily healthy hearts. When we tried to create an infarct model, they were generally unstable and the animals fibrillated, so it was very difficult to get.
Was this a calf model?
Calf model, yes.
Yeah. That's quite an undertaking.
Yes, yeah. So we had a couple animals that we got data on. And then, so there were, certainly contributions to the LVAD, and we were also working on a pneumatic total artificial heart. Before I came to Hershey, Bill O'Bannon was there, who was originally at Baylor and had worked on the drive unit for their very first total artificial heart implant, worked with Dr. DeBakey. Then he had come to Hershey, but was going back down to Texas. So
he was on loan, sort of?
No, that was his position, but I think Dr. DeBakey had decided he wanted to get back into the artificial heart business. So that would have been in 1975, I think, or probably 1975. So I sort of took Bill's place there, and so we worked on the total artificial heart, the pneumatically driven device, and Bill and I also worked on a drive unit. It was interesting that the Thoratec had a pump but no drive unit. So Bill and I did a pneumatic drive unit that went down to Glenn Pennington. So the first patient he did was with a pneumatic driver.
Is that right?
That Bill and I did. This is before Thoratec had their own driver.
So was that a pediatric case or an adult case?
No, that was an adult case, with one of the first pierced tonic eyes. So, and that led to this very similar, two pumps, pneumatic pumps for a total artificial heart. So I guess Barney Clark was done in 1983, I think.
82.
82, okay. So then I think we did our first implant maybe in 1985 with a total artificial heart. We did five of those patients. The first patient was transplanted, but did not survive the transplant. I think several days after he died. But we did 5 of those patients. And also, concurrently, there was this emphasis on a completely implanted system. So we started working on that at the same time. And I think I know we would have continued to use the pneumatic total artificial heart, but the Food and Drug Administration wanted to know what valves we were using. And we were using the Bjork-Shiley, the monostrut valve, not the convexo-concave. And there was very little data about that valve. It was, we had broken the spherical disc valve in our pumps early on, and that's why we switched to the CC valve. And they just wanted so much testing to be able to use that it just wasn't something that we could do. And at the time, I think Shiley was having problems manufacturing valves and dealing with valve failures. So we stopped using that, that device.
So you were under an IDE for those 5 patients? Or?
Yes, there was an IDE for those first 5 patients, but it was, like an inch thick IDE.
Oh, really?
Yes. Yeah.
You ought to immortalize that.
Yeah. We complained about it. So.
Everyone would like to have one that size, I think.
Well, at that time, I don't think they knew what questions to ask. Do you know what I mean? It was new to them. So, but as time went on, they saw various failures and certainly spoke to people at the NIH. They learned more about what questions to ask.
So tell us about the artificial heart program then, and how directions that took in terms of, was Bill still the PI on these?
On the total artificial heart, the pneumatic total artificial heart, and the LVAD, and then I got a Whitaker grant, actually I think for 3 years, to develop an electric motor-driven ventricular assist device. And the very first one of those, we competed in the LVAD contract submission for the RFP and weren't successful. But we continued to work on that under the Whitaker grant. And originally that was a cam-driven system that worked rather well in the calf, but had durability issues. So we switched over to a roller screw drive system. And about that time, brushless motors were becoming available. Before that, everything had brushes and certainly had a finite life. So now, with a brushless DC motor and some of the polyurethanes and proper design, you were looking at a device that could certainly make 2 years. So we decided that we should really look at doing a completely implanted system, transcutaneous energy transmission and implanted electronics. So we look back in the 1969 Artificial Heart Conference proceedings. I'm not sure the actual, it's a big red.
Yeah, Ruth Hagley put that, together. And that, you base things on that?
Well, that had a lot of information. I think it was people from Thermoelectron, Huffman, I believe, had done power transmission, and Dr. Shooter had done transcutaneous energy transmission, so we knew how much you could dissipate. And we had gotten some information from Thermocardio Systems as well on their TET system. So Dr. Bill Weiss started working on a different method of doing that, and actually was able to patent a newer method to do that. So we were able to do one of the first animals, both heart assist and total artificial heart, with completely implanted systems. We originally worked with Honeywell on some lithium batteries, and I think they finally realized that there was a liability associated with artificial hearts. So we wound up going back to NiCads, even though that was old technology at the time.
So what about the patent situation on these, as you were going along? How did you handle that?
That's changed at the university. We would put in disclosures. The reason the Pierce-Donachie pump is called the Pierce-Donachie pump is because the university decided that they didn't want to patent that. And Bill and Jim went to the NIH and said, can we patent this? And at the time, the NIH said, sure, you can do that. So even the Arrow Lionheart, the blood pump and the energy converter really didn't have any patents, but there was a tremendous amount of know-how there.
Things you could trademark or be secret.
Yes, yeah, and the transcutaneous energy transmission had coverage. So I skipped ahead a little bit. You know, the Lionheart was this roller screw based ventricular assist device, pulsatile. It was the world's first completely implanted system. That was done in 1999.
Yeah, those movies that you made of some of your patients were truly remarkable.
Yes, yes. We had some young patients. Gail Snyder was a local man in his 30s that had the assist device, and he was notorious for, you know, taking off his external coil and running on the batteries, and you know, right down to the very last drop too. So.
And how much time was on those batteries? Were they NiCads?
Yes, they were NiCads, and I think that there was at least one patient out 3 years on those, but the run time had gotten down to about 20 minutes. So, so that was a large electronics, container too. So I think that was really one of the issues, was that NiCads, you just couldn't get a reasonable amount of time in a small enough package.
So back to the artificial heart. Where was that going before the Lionheart?
Well, there was a pneumatic device that we did the patients with. That stopped, but at the same time, we'd been working on a roller screw type artificial heart, and we were one of the people that responded to the RFP for the contract for the total artificial heart, and that was, I believe that was around $2 million a year at the time. So we said, if we're going to do this, we need to hire some people and gear up and do some work in the lab. And of course we did that, and as you're very aware, that program then was abruptly halted by Dr. L'Enfant, and right away we had Senator Kennedy and Senator Hines, Senator Hatch, Arlen Specter. Within a week, all of a sudden, these people were all working on this and trying to get those funds reinstated. And as you know, they were successful, but it was really a scary time for everybody, because we had people and we're telling them, gee, we're not sure we have money to pay you. And so it was a good thing that the department at that time could afford to help out, and we didn't actually lay any people off.
But did you have subcontracts outside?
3M was our subcontractor. Bill Pierce had known Dick Sarnes for a number of years, and so that was 3M had purchased Sarnes, so that was the division that we worked with there.
So how did the roller screw come along? Where did you discover that?
I'm not sure who saw it. Originally we tried a ball screw, and with a short stroke, the balls don't recirculate, and it has a limited life. And the roller screw caught somebody's eye, and went to look into it, and we saw it was used in aircraft to actuate flaps or aileron or something. And the more you looked at that and the specifications for it, it looked like it would be a very long-lived system. So all the calculations showed that you'd have a life in excess of 10 years under the highest loads that we would anticipate and at the beat rates that we saw. So that's how we started with that. And that particular system, I don't think we ever had a roller screw. Well, I shouldn't say that. Some of the early ones that we purchased were non-stainless steel, and we did have corrosion issues with those, but then they were made out of a stainless steel material, and there were never any corrosion issues with that.
So you moved on to the Aero system, the completely implantable system. How many patients then were?
I think there were 30 of those patients done. I think the longest was out about three years. That program, at that time, the founder of the company had named another person as president. So Marlon Miller was a founder, Phil Fleck was a president, and I guess after several years decided to retire, and there was a new CEO put into place, and the priority for heart assist devices really changed, and they also tried to get Marlon Miller off of the board of directors, the founder, and I guess he had enough controlling interest in the company to put it up for sale, and the company was sold, and that was the end of the CORAID program, as well as the Lionheart program.
So if you had a clean piece of paper today, what would you think about designing for as a replacement or as an assist system for heart failure?
Well, one of the big issues with these continuous flow pumps, certainly thrombosis is still an issue, but in particular with the continuous flow, it looks like the acquired von Willebrand's disease and AV malformations. And I don't think anybody really understands, they talk about shear stress for the von Willebrand's factor and perhaps lack of pulsatility. So we've been working on a Tesla type pump because it looks like the shear stresses are lower in those devices. So I think
why don't you explain what a Tesla pump is?
Well, Nikolai, Tesla was very famous for his electrical work, but he also did mechanical things. He did a Tesla valve, and it's a valve that will give you one-way flow, but it has no kind of a flap in it or anything. So it's really interesting if you Google Tesla valve. And certainly the Tesla pump is a series of discs that use the viscous forces to propel the blood. So disc spacing and diameter and speed all affect the stresses that are in there. But if you look at the stresses in a Tesla type pump, this disc type pump, versus a bladed pump, the stresses are generally lower just because the surface area is greater. But we still haven't answered the question, does that produce the acquired von Willebrand's disease or not? And that's one of the things. So in terms of designing a pump, I'd look for something that could have pulsatility to it, and then looking at low stresses, but it's stress and time, and I don't know that there's enough data to really go ahead and design a pump from a blank sheet, other than to say, I'd like the stresses to be as low as possible and have them act for a short period of time. But so the idea of going back to a pulsatile pump, I think if you look at the thromboembolic complications with the XVE pump, that it's probably less than the complications that you see with the HeartMate 2. But the HeartMate 2 is so much better because it's so much more durable than than the XVE was. So I think that's the advantage to these pumps. I think, a pulsatile pump, the Lionheart, we ran 14 of those systems for a number of years and demonstrated in excess of 5 years durability. But I would think that you could argue that if you were going to look at the most durable device, a non-contacting, one-moving component like a rotary blood pump should be more reliable.
Well, you certainly did a lot with reliability studies. Do you want to talk a little bit about how you came up with the scheme that you used and how that worked out?
Okay. Well, when we got the total artificial heart contract, and that was actually, to build a completely implanted system, that occurred before our work with ARROW. And as you're well aware, the NIH brought in some consultants. Bud Bureau was the one that comes to mind. And we learned an awful lot about reliability from Bud, and then Rona Shankar was another person from the FDA that came in. So we were given the guidelines, and then we learned about today what's called the quality systems regulations from the FDA. It's a book about that thick, and it tells you how to design and test a pump starting from customer requirements and design requirements and all of your software testing. So we actually went ahead and lived by that document, and to this day we try to do as much as we can in the lab in that way, because it's so important when you go to transfer this technology to a company that they don't have to start all over with the documentation.
Those, like we came to Penn State, all of the artificial heart groups and the consultants, that was like magic, those meetings where we'd have those groups together with Bud and Rona and Jim Anderson, I think, came.
That's right, yes. Oh, yeah.
And Larry, the hematologist, I've forgotten his name.
Yeah, I know who you mean, but I can't remember his last name either.
Well, what was that like, organizing one of those meetings?
It was actually pretty easy. I think initially there was fear on our side because we looked at it a little bit more like somebody coming in and giving you an exam, until we realized that it was partially that, but it was more, we're here to help you, actually, so to encourage you. So we want to see what you're doing, but we're here to help you, and we'll give you, corrective criticism. So I think that really helped. And eventually we had 10 of these systems running, 24 hours a day, 7 days a week. I could go ahead and call up the systems from at home with my computer and look at how they were doing, what was happening with those systems. And we ultimately demonstrated the 80% reliability with 80% confidence for 2 years. It wasn't easy, and we had some restarts, but we were able to do that.
Pretty remarkable.
It is. We had a lot of appreciation for Novacor that had actually done that first, I think, with their LVAD. So
the Novacor system almost fell subject to the San Francisco earthquake, because the room was locked and secured, and when the earthquake started, the systems were vibrating on the table, and no one could get to them because they were all locked up.
Well, as you know, in the 70s and 80s, there was friendly competition for who would have the longest surviving animals.
Yeah.
So we had an animal that was out, I think, close to over a year, when 3 Mile Island occurred. So we started looking at evacuation plans and getting a truck and moving the calf from the animal research facility to University Park to get out of because 3 Mile Island is probably 5 or 6 miles from from the medical center. So that was one of our big concerns. Not how we get our families out of the area, but how we get the calf out of the area.
That's quite a story.
Yeah. So while the Lionheart was going on, as I said, the total artificial heart had completed the contract, and originally there were 4 groups, as you know, and those 4 actually got reduced to 2, Abiomed and Penn State. So when the contract was over, 3M had decided that they weren't going to move forward with manufacturing or commercialization of the device. As you may know, they purchased a biomaterials company that made silicone rubber, never made breast implants, but I think prior to their purchase, that material had been used in breast implants. And I think without admitting any fault, they paid $300 million, something like that, in damages. So when you started talking artificial heart with them, it was pretty clear that they weren't going to move.
They weren't
going to move forward. So we started a company and did a business proposal. The company was called Benecor to commercialize the roller screw total artificial heart. And Abiomed said that they were interested in that. So the technology was sold, actually sold by Penn State and Abiomed. Sold to Abiomed, and that pump went on to be the Abiomed 2. So they took basically the energy converter and modified the blood sac to be like a smaller Abiomed, and got that system up and running. They had several running systems, and I think Scott Corbett told me they had one system that had been running for 7 years. But as you know, Abiomed got out of the artificial heart business, I think, when Impella became a real business for them, and that technology hasn't moved at all. And unfortunately, the way the agreements were written, that's not something that we could, or any company associated with Penn State could pursue, the roller screw total artificial heart. So it's a big disappointment.
Sure. Had they done reliability studies, or they just had run a couple for 7 years?
They had done reliability studies. I'm not sure what the results of that were, but I know that there was one that, and I'm not sure why they just sort of left that one running. I mean, we made a 50cc Lionheart device in anticipation of wanting a smaller device, and that one's running in our lab. It's almost 6 years now. I think that's just been running on a mock loop. So not really reliability data, but nobody has the heart to turn it off, I think. So.
Speaking of hearts.
Yes, that's right.
Well, let's switch gears, if you will, and talk a little bit about some of your personal interests and how you got into it. You like to race cars.
Yeah, that's been a sort of a lifelong thing for me. I don't know. I think it came from when I was just a very young fellow, probably fifth or sixth grade. A friend of mine's father was a local police chief, and he used to moonlight as a security guard at a local racetrack. So I used to go along, and so maybe that's where it came from. I don't know. And then my interest in mechanical things. So when I finally got out of school and could afford a car, I started racing, and I've designed and built four race cars over the years, and I think this year was the 31st year of doing that. So,
well, tell us about the cars. What kind of races do you?
This is SCCA, Sports Car Club of America, and I run in what's called a GT class. So the famous person that was in, I'm in GT2, he was in GT1, was Paul Newman.
Oh.
So I raced in races with him for a number of years, and I think he was 80. Well, he was over 80 years old because his car number, he would change it every year to his to his age, and he was very, very good. He probably could have been a professional race car driver instead of an actor. So, a real gentleman. So we race on road courses like Watkins Glen, Lime Rock, Connecticut. We've raced at Daytona. Road Atlanta.
You've been to Daytona?
Yes, the road course that they have there that they run the 24-hour course on.
So tell us, how many races have you been in, and what's the record?
Oh, gee, I don't know. I mean, I keep results, have a big stack of results in the hundreds of races, and we finished third in the nation in, I think it was 1998 or 1999.
Oh, that's remarkable.
So, yeah. So
terrific.
Yeah, it's still fun, and I enjoy it. I don't have the energy and the time. You know, it used to be I'd come home from work at 7 o'clock at night, go out in the garage, be there till 1 o'clock. You know, although when we had LVAD patients and total heart patients, you'd be in all night and just work through the next day. But now, it's not going to happen. So.
Yeah, I remember having balloon patients at Parkland Hospital, and one year going back 96 times.
Yeah.
1 year, in addition to being there every day anyway. So adds up, doesn't it? So what other hobbies?
That pretty much consumes
the hobby time.
Yes. Yeah. Not much else in hobbies. Interest in students. I still give some lectures. I had gotten a Whitaker grant to develop a biomedical engineering institute at Hershey, and that's still very limited, but that's still in existence today. And developed a course, artificial organs course, I think in 1991, and that still runs today as well.
Do you get interns and students?
A few, not as much as we did. We don't have residents in surgery doing research. I don't think it's a requirement anymore that residents do research. I'm not sure, but we've not had one in the lab for probably 6 or 7 years.
So along the way, where would you put some serendipity developments or occurrences that came along?
Oh boy, that's a tough question. I'm not sure that. I can't think of anything that
surprised you.
Yeah. Well, there were a lot of surprises along the way. The 3M showed an interest in ventricular assists, and since I believe the patent had run out on the Pierce-Donikai, 3M actually made a Pierce-Donikai type pump, and they had a very good relationship with Medtronic, and they didn't want to use the Shiley valve. They wanted to use the Hall Medtronic valve in that pump. So that pump was made with the Hall Medtronic valve. We did a lot of testing in animals, and it looked just fine. And the first patients we did just hemolyzed like crazy. I mean, we had plasma hemoglobins in the several hundreds. So that was a surprise.
That was a surprise.
Yeah, and then we learned that if you see plasma hemoglobins in calves over 10 milligrams %, that you're in trouble.
You're in trouble with
Yes.
humans.
Right. But a human, if you saw that, you'd say, oh, that's fine. But,
The 10 milligrams in humans.
yes.
Yeah.
Yeah. So, and that was about the time that 3M also started to, have concerns about being in a position where they just had such a high chance, such liability exposure.
So what's going on at Hershey these days? And is anyone looking at combination therapies or anything with assisted circulation?
No, I think that at least in our division, the focus has been on this pediatric heart assist device, which is a small pneumatic pump that we've done quite a few lambs with that device, and we've run them after being on heparin for the first few weeks, no anticoagulants at all. These animals have really looked spectacular. I mean, some of the best animals we've ever had. But there's very little interest in marketing that device just because of such a limited market. So we've not been able to find an industrial partner. So we have about a year left on that grant. So we're looking for philanthropy, someone or some entity that would say, well, how much money would we lose every year to help these children?
Uh-huh.
So that's a focus. We're spending a lot of time on trying to optimize the Tesla pump, and also trying to do some basic fluid mechanics studies on the effects of turbulence on hemolysis. The model that everybody uses looks at Reynolds stresses and tries to relate hemolysis to the Reynolds stress, when in fact the Reynolds stress is really an artifact out of averaging the Navier-Stokes equation. So we're looking at dissipation or viscous stresses, and now that you can do large eddy simulation and you don't have to use the Reynolds averaged equations, that they're computationally you can do something to predict the forces on the red cell. So we'd like to be able to do that, and then do that with a von Willebrand molecule to be able to have a tool that you could use to design a pump. Actually knowing what kind of stress and times that you need.
Did you use that on your pediatric?
No.
But you've gotten these really good results.
It's been really sort of optimizing the geometry through trial and error. We did certainly some pulsed image velocimetry. We would build a pump, do PIV and laser Doppler studies, and try to minimize stagnation regions or eliminate the stagnation regions and eliminate the high shear areas as much as we could. We also make our own heart valve for that. The monostrut valve that Shiley made, that was used in the Lionheart. So Arrow wasn't happy purchasing those, so they actually purchased all the documentation and everything to manufacture the monostrut valve. Well, when Arrow got out of the business, we got the design for that valve, so I went ahead and took the frame and made it into a tube valve so that you could have a really good junction between the connector, the valve, and the blood sac, and really reduce that area where you'd have a crack or a crevice and get thrombus formation.
Uh-huh.
So a lot of detail. And also the way we make the sacs has changed over the years.
So how do you make the sacs these days? It used to be pretty crude.
They were done on a wax form covered with a filler-free silicone rubber, and then they were dipped repeatedly with a solvent evaporation process, and then you melted out the wax and pulled out the silicone form. But we changed polymers that had some silicone in the polymer, and then we were able to cast them over polished stainless steel mandrels. So that technique plus some other changes in manufacturing gave us a very smooth surface, no bubbles, and you still had the advantage of having silicone in the material.
So how do you view the federal agencies now that are...
I'm sorry, how do I view the
federal agencies, the NIH, the FDA, and reimbursement?
Well, we wouldn't be where we are today if it weren't for the NIH, there's no question. And I think the FDA also facilitated making better devices. I think without them, I'm not sure what would wind up going into patients. I mean, I look at the first patients we did and the testing that we did, and it was fine at the time, but today it wouldn't be suitable at all, 1976. The reimbursement, I think, is very important. I think, hospitals won't do this if they lose money. I mean, today, if you get a really, really sick patient on an LVAD or a total artificial heart, it can be very, very expensive. And the hospital doesn't like losing $500,000 a patient. So, these programs could disappear if they wind up costing the hospital a large amount of money.
So the implant activity at Hershey, what's that like these days?
I'm not sure. Earlier this year, they had 20 patients on LVADs and one patient at home with a Syncardia total artificial heart. Not sure about the number of transplants, but the LVADs, I think I had mentioned to somebody at dinner the other night that I ran into a patient, Jack Bateman, who had an LVAD 23 years ago and then was transplanted, and he still has that heart today. He was in for hip surgery. But
he was in for hip surgery?
For hip surgery, yes. Yeah. He was complaining about his knee, but it was his hip. So.
And he ended up with
They put an artificial hip in, and he's doing fine, from what I understand.
The most recent time he came in.
Yes.
Yeah, okay.
No, he was in severe heart failure when he when he came in.
I got it confused.
Yes.
Gus, would you like to speculate a little bit on the future and where you see things going, particularly that could eventually have a clinical impact?
Well, I'm optimistic. I think some of the progress has been slow because of the lack of initiatives by the NIH for RFAs to address some of these problems, like the acquired von Willebrand disease and thrombosis. But I think people will continue to work on those areas and eventually be able to reduce those complications. Certainly one of the major hurdles now is that to bring a device to market, it's in the hundreds of millions of dollars. So the next generation of devices is going to have a very, very clear advantage before someone will invest in that. I mean, and it's going to be difficult to demonstrate that these devices are superior until you do a comparison trial with another device. So there's a big financial hurdle there to get out into the market. So that's certainly a concern. But I think these devices will continue to improve. If you look at heart valves or pacemakers and the evolution of them, I think LVADs sort of are following on that path and will continue to move along that path.
Well, thanks, Gus, for your insights and your thoughts and some of the historical things that you've relayed. I know on a personal note, it's always been a pleasure working with you, and you're certainly one of the premier group leaders in terms of pulling a team together and headed off on a mission. So on behalf of Project Bionics, we thank you very much for this personal interview.
Well, thank you very much too, John. Thanks.